This will be my last video from section 9.1, and I'm getting a little tired, so I hope I don't rush it too much. How big should our sample be? How big should n be? What is the ideal n? We have been saying all quarter long that n should be big enough, but then somewhere in the middle of the quarter, then we started going, oh, but not too big. So it turns out to be a relatively fine window. So how big do we need n be to accurately be able to predict our margin of error? So let's start with the formula that we know for the margin of error. I made a mistake there. Hang on. Oops. I forgot the critical value. Oh my goodness, hang on. The critical value is this guy, z sub alpha over 2 times the square root of p hat q hat over n. Okay, time for some algebra. What fun. We're going to divide both sides by the critical value. And so this is what we're going to get. We're going to get the margin of error divided by the critical value is going to be equal to this square root. And now I'm going to square both sides. So I'm going to end up with the margin of error squared. There's a reason why I'm distributing that squaring over the critical value squared. Boy, that looks so mouthy, doesn't it? You should let people look over your shoulder watching you do this. I'll be really impressed. And now what I'm going to do, because I distributed the squaring, I'm going to cross multiply, which is usually people's favorite thing to do. So if I cross multiply, what I'm going to end up with is I'm going to have the margin of error squared times n, and that's going to equal the critical value squared times p hat q hat. And now all I got to do is divide out by the margin of error squared. Now what I have on the right hand side is I've got something squared divided by something else squared. I can now pop out the squaring again. So the critical value divided by the margin of error, and that whole thing squared, times p hat q hat, and that's how big n should be. We now have a specific formula for m. The critical value is based on the confidence level. So if we need a certain amount of confidence, comes from the confidence level. And the margin of error, well, we're going to need a margin of error that isn't too big to not be usable anymore. So this is determined by circumstances. And in your case, it'll be determined by the requirements of the problem. Okie doke. Now you might be looking at this formula. Let me clear the screen and put the formula top and center there so that we can look at it a little more carefully. So that's our formula for n. And you might be asking me, I mean, I've probably trained you at this point. Anytime I give you a nasty formula, then I haul out my calculator and I say, or you can use your calculator. Not this time. That's why we need to be able to find the critical values, because I don't have any other way of finding n except using the formula. So do you need to know this formula? Yes. Know this formula. Write it down someplace safe where you can find it when you need it, and look it up anytime you're asked to find n. So what was I going to say about this? Oh yeah, hang on. P hat, Q hat, please notice I don't know n yet. Not until I've computed this formula will I find out what n is. And if I don't know what n is, I haven't conducted the study. And if I haven't conducted the study, I haven't collected any data. And here's the short version. We don't know p hat. And if I don't know p hat, I don't know q hat either. So what are we going to do? So there's two things that we can do. In the real world, hang hang on. So in the real world, we could use a p-hat from an earlier study. So for example, a homework problem might run along the lines of how big should your sample size be if you needed a margin of error of X and a confidence level of 95%. Suppose an earlier study had found that the true proportion was equal to 16%. So in that case, we would say, for example, p-hat equals whatever it equaled in an earlier study. Or we could do worst case scenario. Which is the biggest p-hat times q-hat could be, which would result in the biggest n that it could be. And it's better to have too big of an n than too small of an n. Too small of an n and we don't end up with any usable data. Too big of an n, we maybe spent a little more time than we needed to, a little more time, a little bit more money. So the biggest these two can be is when p-hat equals 50%, when it's right in the middle of the percentages, which would make q-hat equal to 50% as well, which makes p-hat, q-hat equal to 0.25. So that's worst case scenario. If we can't come up with a better estimate than that, then we'll just plug in 0.25 for p-hat, q-hat. Okay, let's do a sample problem. So a couple years ago, there was a special election in Virginia, and there was the Democrat Ralph Northam, and yes, this is the same Ralph Northam who is in the news lately for embarrassing himself, ran against Ed Gillespie. And 2 days before the election, the polls said that Northam was ahead by 43% and Gillespie had 40% of the vote. The margin of error was 3.5% of the vote. And I don't know if you see what the problem here is. Here's where Northam stands. Northam is ahead. This is Northam. And the point estimate was 43%, but if you tack on the margin of error, the window around this guy is anywhere between 40.5% and 46.5%. Now I'm wondering if I can change color. This might be a mistake. Now the window around Gillespie, here's Gillespie down here. Oh, hey, check that out. He's at 40%, just a little bit below this window here, but the margin of error says that he could be anywhere between 36.5 and, math is messing up here, 43.5%. I'm doing this in my head, I might be messing up. And the true proportion of the people who might be voting for Gillespie could be here. That could be the true proportion of people who like Gillespie. And the true proportion of people who like Northam could have been here. This is what we call in the language of polling, too close to call. That it could be that Gillespie is actually ahead of Northam and we're only 95% confident that maybe Northam's winning, maybe Gillespie's winning. That's all we've got. Our margin of error is too large. Margin of error is too large. So what we need is a margin of error that will split these two intervals into separate intervals on the assumption that the point estimate for Gillespie and the point estimate for Northam are close to the true values. What we need is over here we've got Gillespie and I need a window around him that's smaller than the window around Northam. And so what I'm going to need, it turns out, is the distance between these guys is 3%. And I need to split that window in half, but I also don't want them to overlap. So I want a margin of error 1.4. So we want a usable margin of error the margin of error to be equal to 1.4%. Don't forget that I have to write that as a decimal. So that's what my margin of error needs to be. So let's figure out how big the sample has to be. How big should n be now? How big should n be? Okay, so I want to find my sample size for this poll. Let's say the proportion we're looking for. We're trying to find the proportion of people voting for Northam is what I was going to do, sorry. You can only work on one proportion at a time. Then we'll go back and figure out how many people are going to vote for Gillespie. And what we want to know is what n is. We've said we want a margin of error of 0.014. And let's go for our usual confidence level, a confidence level of 95%. It almost always is. As a matter of fact, if it's not specified, it probably is 95%. The advantage of that is that means we know that the critical value is 1.96. So here's our formula. N is going to be the, what goes on top? The critical value goes on top, divided by the margin of error, that whole thing squared, times some p hat times some q hat. And we do have a p hat from a previous study. We have the study that was done 2 days before the election. Maybe it's 1 day before the election now. So that my critical value is 1.96. My margin of error, we've decided, was going to be 14%. Sorry, 1.4% I meant to say. And in the previous study, we had 43% planning on voting for Northam. And the complement of that is 0.57%. And so when I shove all of that into my calculator, this is going to get me 4,803 people and 96 hundredths of a person. So clearly we're going to round that. And now we're breaking rounding rules. Always round up. It's better to have too big of a sample, because it's just slightly too big of n than too small. Too small, we might end up with overlapping margins of errors. Too big, we spend a little extra money to find one more person. So n is going to be 4,804 people. Now, you would have rounded that up anyway, but no matter what, round up. Okie dokie, that's all I actually think I have time for. I don't have time for my next example. So that's all I've got for you in this video, and that's all I've got from section 9.1.